The A380, an aircraft with a massive maximum takeoff weight of 570 tons. How does it manage to land safely in such fierce crosswinds? The answer is the result of humanity learning from birds. Though we were not born to fly, we have engineered incredibly precise tools, granting ourselves the power to master the air currents just as they do. In this video series, we will explore the working principles behind modern commercial airliners. Fasten your seatbelts. We are ready for takeoff. When we look up at the sky and watch a hawk gliding smoothly through the air currents, or nimbly rolling and turning, what we are actually witnessing is nature's most perfect flight control system. A bird's ability to fly with such freedom doesn't rely solely on the simple up and down flapping of its wings. The core secret lies in a powerful and incredibly precise muscular system. By utilizing these intricate muscle groups, they continuously alter their airfoil shape and the deflection angle of their feathers. We can break down the process of how birds control their direction into the following key phases. Phase 1, initiating intent neural transmission. The flight control center lies within the bird's brain. When a bird encounters a crosswind, or decides to bank left for a turn, the brain instantly generates control commands. These are transmitted as bioelectrical signals along the nervous system directly to the wings and tail. Phase 2, fine-tuned muscular execution, precision actuators. A bird's wings and tail aren't just equipped with large muscles for flapping. They are densely packed with numerous tiny control muscles. When neural signals arrive, fueled by energy from the bloodstream, these small muscles aren't tasked with generating massive thrust. Instead, acting like intricate miniature actuators, they perform minute millimeter-scale contractions and relaxations. Phase 3, altering aerodynamic form, airfoil reshaping and deflection. The contraction of muscles, pulling on ligaments, directly alters the bird's physical shape. First, by changing the airfoil's camber, muscles stretch or contract the wing's leading and trailing edges, altering its curvature to instantly increase or decrease lift in specific areas. Second, through feather deflection. Under muscular control, the primary flight feathers and tail feathers can independently twist, open, or close, much like window blinds. Phase 4, controlling flight direction. Air currents are invisible, but altering the bird's shape redirects the airflow. A slight decrease in lift on the left wing, paired with a slight increase on the right, allows the bird to execute a perfect roll. A subtle upward tilt of the tail feathers forces the airflow downwards, causing the bird to raise its head and complete a pitch maneuver. In summary, in the avian world, the brain is the flight control computer, the nerves are the fly-by-wire circuitry, and the muscles are the ultimate powerful actuators. Once we understand how birds use their muscles to alter their aerodynamic profile, we can perfectly grasp the control logic of modern commercial airliners. On a modern airliner, while the engines provide forward thrust, it is the hydraulic system that truly enables these multi-hundred-ton behemoths to perform takeoff rotation, execute mid-air turns, and maintain stability even at complex high-altitude airports or in strong crosswinds. The pilot's control stick commands are translated into electrical signals. High-pressure hydraulic fluid acts as the aircraft's bloodstream, delivering energy to the various hydraulic actuators. These actuators serve as the airplane's muscles, powerfully driving the ailerons, elevators, and rudder, and extending the slats and flaps. It is this system that allows us to firmly command every attitude of the aircraft. How did this entire intricate hydraulic control system evolve? This history of development is essentially the story of humanity continuously building muscle for aircraft in order to conquer higher speeds and greater weights. We can break down this evolution into 4 key stages. 1. The purely mechanical era, the pilot's hand-to-hand combat, early days to 1930s. Flight control relied primarily on steel cables, pulleys, and pushrods. Because early aircraft were slow and light, the control stick was directly linked to the control surfaces. Pilots relied entirely on sheer arm and leg strength to battle aerodynamic resistance, much like trying to steer a bird by manually pulling on its feathers. However, as aircraft grew larger, this pure manual approach reached human physiological limits. In severe turbulence, the aerodynamic forces could violently kick back through the controls, sometimes even breaking a pilot's arms. humanity desperately needed a force amplifier. Phase 2, the introduction of hydraulics. The exoskeleton as an auxiliary support, 1930s, end of World War II. Low-pressure hydraulic systems, approx. 1,000 to 1,500 PSI, made their debut. With the emergence of all-metal monoplanes like the Douglas DC-3, aircraft became exceptionally heavy. Hydraulics began to serve as heavy lifters, primarily responsible for landing gear retraction, flap operation, and braking. However, primary flight control still relied on steel cables. During this era, hydraulics were more like auxiliary muscles, providing occasional power where it was needed most. Phase 3, the era of fully powered hydraulic control, the steel muscles breaking the sound barrier, 1950s, 1970s. Entering the jet age, aircraft speeds pushed toward the sound barrier. Aerodynamic forces became incredibly violent, acting on the control surfaces like solid concrete. To overcome this, mechanical commands paired with fully powered hydraulic actuation, running at 3,000 pounds per square inches, became the industry standard. Pilots now use steel cables simply to open hydraulic slide valves. Instantly, high-pressure fluid would surge into the actuators, unleashing tons of pushing force. In fact, these hydraulic muscles were so overwhelmingly powerful that moving the control stick felt almost weightless. As a result, engineers had to invent an artificial feel system to artificially add resistance, simulating aerodynamic feedback to prevent pilots from making sudden, aggressive maneuvers that could literally snap the aircraft apart. Phase 4, fly-by-wire and modern hydraulics, the perfect synergy of nerves and muscles, 1980s, present. Modern large commercial airliners like the A330 and other wide-body jets severed the heavy, friction-prone steel cables of the past, replacing them with slender electrical wires. Pilot inputs are now transformed into digital electrical signals, calculated by flight control computers, and transmitted to electro-hydraulic servo valves, EHSVs. These servo valves dictate the flow of 3,000 pounds per square inches hydraulic fluid into the actuators. This achieves a flawless separation between neural transmission and muscular actuation. For ultimate safety redundancy, commercial jets are equipped with multiple, completely independent hydraulic systems, typically designated as the green, blue, and yellow systems. Even if one system bleeds out, the surviving systems guarantee the aircraft can safely return home. So, what exactly is a hydraulic system? Humanity's ingenuity in using fluids to transmit energy actually dates back thousands of years. Imagine an ancient water wheel at a riverside mill. The Earth's gravitational potential energy is converted into the massive kinetic energy of the rushing river. This water crashes against the wheel, driving the heavy millstones inside to grind grain. In this setup, the energy source is the river, the transmission medium is the water, the actuator is the water wheel, and the object of work is the millstone. This is the most primitive form of fluid power transmission. The fundamental principle driving a modern airliner is exactly the same. The only difference is that we have to artificially generate this river. Ancient water wheels utilize the kinetic energy of flowing water. This is known as hydrokinetic transmission. Modern aircraft, however, rely on advanced hydrostatic transmission. Engineers trap fluid inside completely sealed metal pipes, taking advantage of a formidable physical property of liquids: their incompressibility. This brings us to the absolute soul of the system, Pascal's law. Because fluid in a sealed circuit cannot be compressed, pressure applied at one end of the pipe is transmitted undiminished and can even be significantly amplified to the other end. The simplest everyday example of this is the braking system in a car or a bicycle. Think about traditional mechanical bike brakes. A lack of lubrication or a frayed cable makes squeezing the lever incredibly difficult. A hydraulic brake, on the other hand, relies solely on the seamless transfer of pressure. It is elegantly simple and entirely eliminates mechanical friction. Braking a bicycle is easy enough, but what about bringing a massive airplane to a dead stop? Is the physical strength of a pilot's feet really going to be enough? This is exactly where the force amplification principle of Pascal's law comes into play. If you apply a force to one piston in a hydraulic system, it creates a specific pressure within the fluid. Because this pressure remains completely constant throughout the sealed system, remember, pressure equals force divided by area. If a second piston has 10 times the surface area of the first, the resulting force acting upon it will be multiplied by 10. It is, quite literally, a mechanical force amplifier. Put simply, a hydraulic system is an artificial circulatory system. It uses pressurized fluid to transport energy and amplify force within a closed loop. Now, let's map our ancient water wheel directly onto a modern airliner. The energy source is now the engine-driven hydraulic pump, generating a staggering 3,000 pounds per square inches of pressure. The transmission medium is high-temperature resistant aviation hydraulic fluid. The actuator has become the heavy-duty metallic hydraulic cylinder, and the object of work, the massive, incredibly heavy flight control surfaces. With a mere flick of the control stick, the pilot commands this high-pressure fluid to instantly unleash tons of mechanical thrust, effortlessly moving the aircraft's rudder or ailerons. The vast majority of modern commercial airliners utilize an architecture consisting of 3 completely independent hydraulic systems. Within each of these systems, you will find the following core components. Number 1. The drive pumps. These convert mechanical or electrical power into hydraulic pressure and fluid flow. Let's take the Airbus A320 as an example. The left engine drives the green hydraulic system pump. AC Power 1, or the emergency ram air turbine, often called the RAT, drives the blue system pump. The right engine drives the yellow system pump, though AC Power can also drive a secondary yellow electric pump. Fascinatingly, there is even a manual hand pump on the exterior of the aircraft that can pressurize the yellow system. This is typically used on the ground by ground crews to manually open the cargo doors from the outside. Number 2. Hydraulic motors. Acting as the receiving end, these convert hydraulic pressure back into mechanical force. Think of it this way. A pump converts mechanical energy, like the spinning gears of an engine, into hydraulic energy, creating that massive 3,000 pounds per square inches of pressure. A motor does the exact opposite. It takes that 3,000 pounds per square inches high-pressure fluid and uses it to drive internal swashplate pistons or gears, transforming fluid power back into raw, powerful mechanical rotational force. On an aircraft, where every inch of space and every ounce of weight is critical, you often need massive rotational torque for heavy tasks, like deploying the wing flaps. Achieving this with an electric motor would require a unit that is shockingly large and incredibly heavy. For the exact same volume, a hydraulic motor delivers several times the torque of its electrical counterpart. Furthermore, there's the critical issue of jamming. If a mechanical component gets stuck, a traditional electric motor will quickly overload and burn out or even catch fire within seconds. A hydraulic motor, however, is completely immune to stalling. If the load is too heavy and it cannot turn, the pressurized fluid simply bypasses safely through a pressure relief valve. The motor itself will never overheat or destroy itself. In aviation, this intrinsic fail-safe is a vital, life-saving advantage. Number 3. Hydraulic actuators or cylinders. These are frequently used for single-stroke mechanisms such as operating the landing gear doors or engaging the wheel brakes. You can picture it acting much like a simple syringe. It operates entirely on fluid pressure. In these specific applications, there is virtually no hydraulic fluid returning through the loop, meaning the overall fluid flow rate is exceptionally low. Hydraulic systems power the core functions of the aircraft. This is the A330 hydraulic distribution chart, which illustrates exactly what these systems can achieve. Every deflection of the aircraft's control surfaces is driven by hydraulic power, alongside thrust reverser deployment, the extension and retraction of flaps and slats, and the operation of the landing gear and wheels. Specifically, the green system is responsible for landing gear retraction and normal braking, while the yellow system handles nose wheel steering, as well as alternate and parking brakes. This covers nearly every aspect of flight control. Beyond that, hydraulics also manage various aircraft equipment operations, such as the opening and closing of the cargo doors. On the new generation of flagship airliners, such as the Airbus A350, the aircraft's muscular architecture has undergone 2 fundamental evolutions in the pursuit of extreme weight reduction and maximum efficiency. First, the A350 increased the operating pressure of the central hydraulic systems from 3,000 to a staggering 5,000 pounds per square inches. Simultaneously, the A350 made the bold design choice to eliminate the third central hydraulic system, leaving the entire aircraft with only 2. To compensate for this redundancy, engineers equipped the key control surfaces with EBHA's, electrical backup hydraulic actuators. This hybrid architecture of fly-by-wire plus localized microhydraulics not only drastically reduces the weight of the airframe, but it also elevates flight safety through absolute physical isolation. From the brute force of mechanical cables to the surging power of 3,000 pounds per square inches fluid, and finally to this highly integrated electro-hydraulic next-generation architecture, this is the modern aviation industry's ultimate answer to safety and efficiency. From the muscles of the natural world to the hydraulic arteries of industrial ingenuity, these are the true muscles of the aircraft. Concealed beneath a skeleton of steel, they operate with breathtaking power and precision, safeguarding every safe takeoff and landing we make. In our next video, we will dissect the environmental system to reveal the hardcore engineering that keeps us alive in the death zone. Please subscribe to my channel and stay tuned for the next video.